Okay, so we continue with Max Wiesner on constraints on the species scale and the spectrum of states in quantum gravity. Please.
Thank you very much. Okay, microphone is on. And first of all, let me thank the organizers for putting together this wonderful conference. I'm really looking forward to this interesting program and to a lot of interaction and talks here during this week in this beautiful venue at CERN. So I want to talk about some work that has been appeared over the last year in collaboration with Damian van der Heijstek, Kumran Waffa, and David Wu from Harvard, and also a more recent paper that appeared a month ago or so together with Alec Bedroya and Raj Mishra. And it's about the species scale and the spectrum of states in quantum gravity. So let me start. If we would generally ask, okay, what is the scale at which we expect quantum gravitational effects to become important, one would probably say it's the Planck scale, so 10 to the 19 GeV, something that even the probably FCC cannot probe. So the question is, what is the actual quantum gravity? Can it actually be lower than the Planck scale, or is it always given indeed by the Planck scale m Planck? And this was already discussed in like 15 years ago by Dwali, who said that in the presence of a large number of light species of states, the quantum gravity cutoff can be made parametrically smaller than the Planck scale. So that's what he called the species scale, and which is basically, in Planck units, a certain power of the light number of species. So if we can make this number of light species very large, then we could indeed make the quantum gravity cutoff, or the species scale, very small in Planck units. But this is, of course, the arena where the distance conjecture comes in, which tells us that if we go in the scalar field space that Miguel already had in his talk, and we traverse a large distance, then an infinite tower of states becomes light in Planck units. So if we go to such asymptotic limits, we would get a large number of states, and hence also the species scale should asymptotically go to 0 in Planck units. And of course, this tower of states is known in explicit cases, and we can hence compute lambda s, or the species scale, in these cases. And there's been much work on this as reviewed in these reviews, and especially on the species scale there has been in the last year. I just basically cited everything that came out after these reviews here. As you can see, there has been a lot of action. So the question is then, of course, if we know how to compute it asymptotically, because there has been a lot of work, we know how to compute the tower of light states in this limit, so we can have different directions, different infinite distance directions in the moduli space, where we get infinite number of light states, and the species scale goes to 0. But what about the interior? What about the interior? Can we actually make the species scale as high as we want, or what is going on there? To answer this, and if we would use the prescription of the species scale in terms of the number of light states, we would actually need to compute the light spectrum at any point in field space. But this is, of course, a very tedious and, in most cases, actually not very promising avenue to proceed. So the proposal we put out in this work with Damian, Kumran, and David is that actually the quantum gravity cutoff should be captured by the gravitational higher derivative corrections to the Einstein-Hilbert action. So if we take the normal Einstein-Hilbert actions coupled to some scalar field phi, we would expect that the higher derivative corrections made up by Riemann and derivatives thereof to have some field-dependent Wilson coefficient. And the proposal is then that these Wilson coefficients of the higher derivative terms should give indeed the species scale. But what is actually the physical meaning of this scale suppressing the higher derivative terms? One may ask, and we can compare it, for example, to field theory. If we take electrodynamics in d dimensions, we also expect higher derivative corrections, which are sensible to particles of a mass m that has been integrated out. For example, if we integrate out the electron mass below a certain energy scale. The analog terms to this would now in gravity should now actually be curvature terms, like r to the n for as an example. And now the suppression should be the species scale to some certain power. But of course, in gravity, we cannot just simply integrate in the additional states like the electron and continue with our lives and just have electron, or in the example of electrodynamics, have now electrodynamics with a corresponding state. But here, since the black holes, which should eventually become the states, are strongly coupled, we cannot just integrate in these states and continue with the effective description. Still, the higher derivative corrections, and this is what I will show in the following slides, should encode the imprint of the minimal black hole that we can describe in the effective theory. This was already the original motivation for the species scale, where Dwali said that in the presence of a large number of states, actually the smallest black hole should have a large entropy, so hence there should be a minimal black hole with a radius bigger than the Planck scale that can be described. And this minimal black hole is the smallest black hole that is describable within the effective field theory. Has some mass m, min, and some radius or temperature lambda min, which is the EFT cutoff, which in general don't have to agree. So to actually see that this higher derivative corrections encode the imprint of the minimal black hole in quantum gravity, what we did is we considered two scattering amplitudes. So what did we do? The main result, and this is in this recent paper with Alec Bedroy and Raj Mishra, we looked at minimal black hole contribution to two scattering amplitudes and showed that they can only be reproduced actually if we have corrections to the higher derivative terms. In this case, we've just focused on these simple examples that are suppressed by this minimal radius of the minimal black hole, which we hence should indeed identify with the species scale. So how did we do this? We looked at center of mass energies that are way above the black hole threshold and at small impact parameters way smaller than the minimal black hole radius. In this regime, one would expect that the scattering process involves black hole formation and evaporation, and hence the amplitude should be exponentially suppressed by the black hole entropy. Now, if we Fourier transform the small impact parameter to fixed angle scattering, so we go from the impact parameter to Mandelstam T. And are still at large energies, the black hole contribution is still suppressed, but it leaves a phase factor imprint. This was actually argued in this paper by Giddings and Sridnicki in 2007. So, and where RH is here the horizon of a Schwarzschild black hole at some energy scale E. This becomes now exponentially large upon analytic continuation in the unphysical regime, where we then get this kind of expression, which becomes actually dominant. And what we then argued is that actually if we match this, if we now go to the black hole threshold M min, what we should effectively do is replace this radius, Rs of E or RH of E, by some critical impact parameter, or by some critical BSC, which is just given by the radius of the minimal black hole, such that the amplitude actually in this regime between M min and lambda min should just be exponential with the exponential determined by lambda min. So when we then go further down to actually the scale lambda min, which is until where we trust the EFT, we showed that in order to reproduce this exponential behavior that we have in the amplitude, what we need is indeed a correction to the higher derivative term, higher derivative term that indeed goes with the inverse of the minimal radius of this black hole, of this minimal black hole. And if we compare this to the species scale definition, what we get is that we indeed find higher derivative corrections that are suppressed by the species scale, and we should just view the species scale as the radius of the smallest black hole that we have, or for which we have an EFT description in the theory. So with this preparation, what we can do is, okay, we can look at the concrete higher derivative corrections to a given AFT, so we have this higher derivative expansion, and now, as I said before, the Wilson coefficient should just encode the field dependence of the species scale. So, and the strategy is, because in general we do not have all these terms, and in particular we do not have all the terms, the field dependence of all these terms at our disposal, we should focus on terms that can be computed explicitly for any value of the scalar field phi. For example, because these are BPS couplings that are protected from loop correction or you name it. As an example, this would be an R⁴ coupling in theories with maximal supersymmetry, or the R² term in the vector or tensor sector of theories with 8 supercharges in 6D, 5D, and 4D, for which we can also explicitly compute the field dependence of these couplings. And in that way, we obtain an upper bound for the species scale, which is valid everywhere in modular space, so we do not have to rely on the asymptotics to actually infer what is the quantum gravity cutoff. So as a simple example, we can consider Tendu type 2A string theory, where we have a single modulus, which is the string coupling, and there the first non-vanishing term of the higher derivative corrections is the T8 R⁴ coupling, because the other couplings are just, or the lower dimensional couplings are just forbidden by supersymmetry. So there we have this A4, which depends on the single modulus, and this one is one loop exact. So it just gets a tree level and a one loop contribution, which have been computed a long time ago by Green and Verhoeven. So we have these two terms in the higher derivative, in the Wilson coefficient of this higher derivative coupling. And so what for the species scale, this of course just means there are also just two terms in this in the expression for the species scale, which are plotted here on the right side. So we have the one loop term. It, of course, dominates for phi going to minus infinity, and there, actually, the species scale that we compute in this way simply agrees with what we expect from perturbative type 2A string theory. On the other hand, the one-loop term dominates in the strong coupling regime, and so we can just get from the one-loop term of the type 2A higher derivative action, we just get basically M theory, because this precisely agrees what we expect for the species scale for one-dimensional decompactification to M theory. We can repeat this analysis for a large class of examples, basically following the list that Miguel had previously. So we can look at 32 supercharges by putting M theory on some torus, 16 supercharges, for example, heterotic and type 1 on some torus, and also for 8 supercharges where we have FM or type 2 theory on Calabi-Yau threefolds. We always find that higher derivative correction, or we find a protected higher derivative correction that capture the dependence of the species scale on part of the moduli everywhere in moduli space. And in particular, we can determine what was coined the desert point in this paper by Cody Long, Miguel, Kumran, and Irene, which is the point in moduli space where the species scale is maximized, or conversely, we have the least amount of light states, which in the example of type 2A, in 10D is just here. It's not actually at phi equal to 0, but slightly shifted, because, I mean, it's not a self-dual point phi equal to 0. And we can go do this in all examples. And what we find is, if we look at the supersymmetrically protected term, we always find that the value of the species scale at this desert point is always bounded from above by the Planck scale. And as you can see, it's just actually always below the Planck scale, such that this is indeed a reasonable upper bound for the quantum gravity cutoff. Another question is, now that we have determined where is the species scale maximized, is how fast can lambda s vary as a function of the scalar fields? This is what we investigated in this paper. And then we can give like a field theory expectation where we would expect this variation of the species scale to be bounded from above. Therefore, consider again this higher derivative expansion, where we have here some operators n or n of the curvature. And we can now integrate out the high energy modes for the scalar field phi, basically the ones that correspond to distance modes that are smaller than the species scale itself. This would generate a new operator, O tilde, with a coefficient depending on the derivative of lambda s, simply by expanding the lambda s of phi around this VEV phi naught. And now the consistency of the effective higher derivative expansion leads to a universal bound, just that this should be bounded by an order 1 constant in Planck units. And this bound should be valid everywhere in field space, but we might ask, what is actually this constant C that we, from a purely field theoretic analysis, cannot fix? There we can go again to our examples. For example, the type 2 10-dimensional. We have here a minimum, of course, of the slope, which is just the desert point that I had before, but indicated by the star. And we have two directions. We have the M theory direction for large phi and the type 2A regime for large negative phi. And what we actually find, not just in this example, but in all examples, is that the slope is maximized in asymptotic boundaries, and the bound is satisfied if we set the C to be 1 over d minus 2. This we found in a large class of examples in these recent papers. So we found that the species scale varies most rapidly in asymptotic limits, and also the bound on the species scale can be, in Planck units, can be saturated in these limits. So, but the possibilities for asymptotic limits is actually very constrained, at least in flat space, by the emergent string conjecture, which was put forward by Lilech and Weigand here at CERN 5 years ago, saying that at any infinite distance in field space, the lightest tower of states predicted by the distance conjecture is either a KK tower signaling a decompactification to a higher dimensional theory, or the tower of excitations of a fundamental perturbative string. And actually, if we believe this, one can now, the nature of this tower now determines the properties of the species scale as well. For example, for a KK tower, the species scale is simply the higher dimensional Planck scale, and by dimensional reduction, we can see what is the slope of the species scale in this asymptotic limit, just given by the simple expression involving the higher dimension and the lower dimension, d and d. If we have a string tower, the species scale is simply the string scale, and then just from perturbative string theory and by the effective action that we get from perturbative string theory, one can easily see that the slope is indeed given by 1 over d minus 2, which is precisely the bound we found. So the emergent string limit gives us the most extreme variation for lambda s just by comparing this coefficient. And so the emergent string conjecture gives us a sharp bound on the slope of the species scale that should be valid everywhere in field space, even though we just used the asymptotics to find the concrete bound. The concrete bound was found by using the asymptotics, but it should be valid everywhere in field space. So just an overview, the species scale can be computed from higher derivative corrections to the Einstein-Hilbert term, corresponding to the scale of the minimal black hole. In explicit example, we can give upper bounds on the species scale in terms of protected, e.g. supersymmetric terms. Gives us also a bound on the maximally possible value for the quantum gravity cutoff, which is coined the desert point. The slope of the species scale is bounded from above everywhere in moduli space, and the bound is saturated in asymptotic limits where the emergent string conjecture predicts a universal bound. So the emergent string conjecture is really a key ingredient here to find a bound that is valid everywhere, not just in the asymptotic limits of field space. But so the emergent string conjecture itself is motivated, and that was, for example, also in the original paper, from evidence from top-down string theory examples. So the emergent string conjecture states that in asymptotic regimes, where we basically can make the species scale smaller than the Planck scale, that is my definition of asymptotic regimes or gravitational recoupling regimes, that these have universal properties. Namely that we either get a KK tower or a tower of excitations of a fundamental perturbative string. But the motivation and the evidence comes mostly from top-down string theory examples. So the question is, can we argue for such universal properties that we have in these weak coupling limits without directly using string theory, but just using it from the bottom up? And this is that was our goal in this recent paper with Alec and Rashmish. And we wanted to show a slightly weaker statement, namely that in any gravitational recoupling limits, which I define as the limit where the species scale is much smaller than the Planck scale, the lightest tower of states is either a KK tower or a tower for which the density of one particle grows exponentially. So we have so rho of E, the density of one particle states grows exponentially, so some kind of Hagedorn behavior as we know it from perturbative strings. And let me stress that there's a complementary bottom-up approach to the emergent string conjecture that was put out late last year by Ivano Basile, Carmine Montella, and Dieter Lüst from Munich. So how do we argue for that? The central object for our analysis is the density of one particle state. And in these limits, in these weak coupling limits, a good estimate for rho of E is given by high energy 2-to-2 scatterings at fixed and small impact parameter. And the general expectation is that rho of E is an exponential of some polynomial, or more explicitly, the logarithm of rho of E should be up to logarithmic corrections, a polynomial of some degree alpha, where alpha is a piecewise constant function on energy. And the idea is to track alpha as a function of energy to infer the properties of the towers of states. And the basic result is that it has universal properties in these weak coupling limits that are summarized in this slide. So we have an EFT regime, a string-like regime, and a black hole regime. And let me dissect this graph by looking at the different regimes. So first, at very high energies, the density of one particle state is dominated by black hole microstates. And so just from the normal entropy formula, for example, for Schwarzschild black holes, you see that this alpha should be bigger than 1. Or more generally, what we argue is that one particle states are black hole microstates if and only if alpha is bigger than 1. Hence, there needs to exist an energy scale at which we go from alpha smaller or equal to 1 to alpha bigger than 1, which should just correspond to the mass of this minimal black hole that I had on my earlier slide. However, this minimal black hole or this highest temperature black hole does not necessarily need to be a d-dimensional Schwarzschild black hole, as recently also pointed out by Alec, Kumron, and David. Because below a certain energy scale, there can exist a solution that is entropically favored over a d-dimensional Schwarzschild black hole. So, which means that if we have a black hole whose horizon is smaller than some critical R star, we should have a transition to other solution. And in string theory, we also know what are the examples. For example, the Gregory-Laflamme transition to higher dimensional Schwarzschild black holes, where this R star is just the KK, inverse KK scale, or the Horowitz-Polzinski transition for perturbative strings. And so the scale, lambda BH, which is just the inverse of this critical radius, is in this cases related to the lightest towers in the asymptotic regime, either the KK tower or the string scale. And so Bedroyer, Waffe, and Wu, they argued that actually this should be a third universal scale in general theories of quantum gravity, which in the asymptotic regime should just give the tower of the mass scale of the lightest tower. So the question is that, okay, what do I actually need to get a black hole that is entropically favored over a d-dimensional black hole? And for that, we considered a d-dimensional EFT of gravity in asymptotically flat space with finitely many weakly coupled states. So in the asymptotically flat space, we can use the weak energy condition, which means that T00 is smaller or equal to 0. And we can consider spherically symmetric black holes, for which then, such that the asymptotic mass is given by some m. So this, if we just impose the weak energy condition, this is the constraint we get on the parameter lambda that appears in the matrix. And now the boundary conditions actually imply that the e to the 2 lambda of this guy is always smaller than the one for the corresponding Schwarzschild black hole of the same mass for NB radius, meaning that the radius of this black hole is bounded from above by the Schwarzschild black hole, such that no black hole should have a bigger entropy than the Schwarzschild black hole. So to get entropically favored state, we need infinitely many additional states, which actually means that this transition scale lambda black hole is indeed associated to the scale of the mass of a tower of states, which is consistent with the proposal Betreuer-Wasser and Wu. One can now ask, what kind of states can I get? And by a tower of state, I mean an infinite family of states with some mass m0 plus some function f of n of the excitation level or whatever times delta m. So what kind of tower of weakly coupled can we get with a mass scale that is way below the species scale? And from the basic properties of the species scale, namely that it's an EFT cutoff from lambda s, that is the cutoff of an actual EFT. We know that there exists an EFT that is described in terms of finitely many fundamental fields and defects that collectively account for all states below lambda s. And weakly coupled defects can give rise to tower of weakly coupled states if they are, for example, in a closed configuration, for example, upon compactification. And by weakly coupled, we mean here that the self-energy is negligible to its tension. For example, the extrinsic curvature should be smaller than the tension. And what we show is actually that the tension of such weakly coupled p-branes for p larger or equal to 1 is always bounded by the species scale itself by considering basically the contributions of these branes to scattering amplitudes. So weakly coupled defects cannot give a tower of weakly coupled states with mass parameter m0 much smaller than the species scale. And so what are the possibilities that we are left with? Since we have an EFT that is valid at 2 lambda s, we can take a weak coupling limit, or we can consider this EFT that we get in the weak coupling limit where we take the lambda s much smaller than the species scale. And since the EFT is valid at energies lambda s, the partition function has to be finite if we put it at a thermal circle, which basically tells us that we should have finitely many weakly coupled states. And then the only way to get a tower of states with mass scale m not below the species scale is if these are KK states. So below lambda species, we can only have KK states. In the deep UV, we have black holes. So we now need to somehow so we have the regime below lambda s and above the black hole threshold, so the UV and the deep IR regime. And we have an EFT description that is valid up to lambda s, and we have a black hole description that is valid above the black hole threshold. And now if we consider the temperature diagram, we basically have that we have an EFT that is valid up to lambda s with finitely many states, so we can consider a system of radiation in a box with an energy up to lambda s and temperature T. And we have a minimal black hole that has temperature T, which is also lambda s. And now the name of the game is to connect these two regimes in a consistent way. Since we have at both ends, we have the temperature given by lambda s, and to consistently connect these two regimes, we consider first the density of multiparticle states, which is of course related to the inverse temperature by this derivative. And we can also parameterize it similar to the one particle density as the logarithm of it as some polynomial in alpha omega. Since alpha omega bigger than 1 corresponds to black holes, we need in this middle energy regime, we need that alpha omega is smaller or equal to 1. And the only possibility to achieve this, since at both ends we already have the temperature to be the same, is alpha omega to 1. And then the final step is to just say, okay, actually if we have omega or log omega being linear in E over lambda s, also the one particle density of one particle's density needs to be linear, or the logarithm of it needs to be linear in this energy regime lambda s until the black hole threshold. Which means that indeed we get a string-like regime where this alpha is equal to 1, which means that we get a Hagedorn-like behavior in this regime. So there are two possibilities. The lightest tower is either a KK tower with a mass way smaller than lambda s, or in the absence of a tower, the lightest tower of states has exponential degeneracy, which is of course the reminiscent of Hagedorn behavior of a critical string. And we can compare this to emergent string conjecture, which precisely predict that the infinite distance limits will either get KK towers or the excitation tower of a critical string. And hence our results provide a bottom-up evidence for such a binary choice, meaning that in these asymptotic recoupling limits lambda s, we either have KK tower or string tower. Though from the bottom up we do not yet see why this should always be a fundamental string. And in summary, I talked about the species scale, which encodes crucial information about the quantum gravity and is calculable via higher derivative terms. In explicit examples, we can give an upper bound for lambda s by looking at terms that are protected by supersymmetry. And we can give a bound that is for the maximally possible value of the quantum gravity cutoff. We found that the slope of the species scale is bounded everywhere in moduli space, where this coefficient d-2 is actually imposed by the emergent string conjecture. And in gravitational recoupling limits, what we then showed is that the density of one particle state has a universal behavior. And from basic properties of gravity, like black hole thermodynamics and the scattering amplitudes, we argued that the lightest tower of states is either a KK tower or has this exponential degeneracy, which provided bottom-up evidence for the emergent string conjecture, which of course was very important to get this universal bound. Thank you very much.
Thank you very much, Max. Please.
Species bound defined within, including the overall coefficient? Is the species bound defined including the numerical coefficient?
Yes.
What's the definition?
So in the explicit examples, what we did is, so for example, type 2a, the example, the overall coefficient would be set such that we know what it should be in M theory. In M theory, you can compute it. It should be the Planck scale. And we actually match it with that, and that sets the overall coefficient from the higher derivative terms.
So it's defined through the coefficient of the higher derivative term?
Yes.
Okay.
One more question.
Yeah, in the context of string theory, there are higher derivative corrections that depend on the derivative of the dilaton as well as the NS flux. Have you taken them into account in your analysis?
So in the dilaton, of course, is taken into account because that was in my example just the simplest case. The flux we have in the examples we looked at, we have not looked at these, but of course that should be doable.
And one comment is that the weak energy condition is T00 bigger or equal to 0.
Yes.
More questions? Observations? There is one from Zoom.
Yes, I read it out. Does this kind of solutions with lambda s much smaller than Planck mass limit the number of possible solutions in the string landscape considerably?
Can you repeat the question?
Does this kind of solutions with lambda s much smaller than Planck mass limit the number of possible solutions in the string landscape considerably?
No, I mean, in the string landscape, we typically have, if we do perturbative string theory, that's anyways what we get, that the species scale is much lower than the Planck scale. So I wouldn't say that it lowers the number of solutions.
More questions from the hall? Yes, please.
Could you please repeat again, what is the bound on the Wilson coefficients that you get starting from the high energy fixed angle universal suppression of black holes? What is a precise statement about the Wilson coefficient starting from this high energy?
So from the Wilson coefficient, so we start, let me go back to that regime. It's basically a two-way matching procedure. We say, okay, we match it so in this energy range above lambda min, we say, okay, there should be, if we go to this unphysical regime, the amplitude should be exponential with this coefficient lambda min to the -1. Then we just say, okay, if we actually we trust this amplitude should be even valid in the regime around lambda min, where we can match it with the expectation from the higher derivative correction. And then just a very rough argument to say, okay, to reproduce such an exponential amplitude that's on the top of the slide, the higher derivative coefficients, like this lambda min. So the crucial point is that I want to see how does the lambda min appear in the higher derivative corrections, because that should encode the moduli dependence of the higher derivative correction. And just by comparing these two amplitudes, we say, okay, it should appear precisely to the correct power that we would expect for the species scale.
Thanks.
Any final comment? If not, we thank Max again.